Hi, Keith here. In this video I'm going to look at some of the options for PERMANOVA in Primer. Now I'm not going to do them all. I'm going to do some of the ones people are most likely to look at and think about changing. And then in later videos I'll look at a couple of the others which require a bit more discussion to illustrate what they're on about. As I often do, I'm working with my simulated data because this allows me to create data sets to match and display particular things, particular points of interest. So you can see I've got two on the left, just 2 replicates per site versus 10 replicates in the map on the right. And to remind people of the scenario, if they haven't watched previous videos, we're looking at a map of a marine environment with 3 oil platforms which may be leaking oil to the environment. There is current from north to south, so if there's any oil leaking it will spread southwards. That's why the replicates are downstream of the platforms. And the bottom goes from about 25 meters deep here to 75 meters deep here. And as we go down the depth gradient, the sediments get finer and have more nutrients. So here is the 2-factor file. I've got labels in the first column here, but that I can use to label the points on any maps or ordinations I draw in Primer. The X and Y coordinates there, the environmental variables, some summarized biological variables, and the actual biological variables across here, different species of crustacea, mollusk, and worm. And these are counts of numbers of individuals in each of the replicate samples. And all of this data is invented and simulated, and I'm just going to use the biological data today. I'm not going to worry about the rest. Here exactly the same for the 10 replicate scenario, and if I scroll across to the side you can see I've got a blank column and then I've got 2 columns with indicator or categorical variables for the factors. The first one is IVC, impact versus control, although I'm using the term ref now for reference, which is increasingly becoming used instead of control. Control is not quite right. We're really using these other sites as a reference for comparison to the potential impact. And then site pair is north versus south. Okay, here's Primer, and I've already imported both of those data files there, and I've selected just the biological variables. Now, before I do analysis, I could consider whether I should transform. So up here, if I go pre-treatment, transform, for this type of data, square root would probably be the choice, or possibly log x. But I'm just going to go untransformed for this particular occasion. Sorry, I'm going to go untransformed, so I'll get rid of that. And what I need to do then is, of course, calculate the similarities. And for biological data, Bray-Curtis is the default. This is just a warning to let me know that I haven't done any transformation, but that's okay, that's what I want. So now I'm going to do the PERMANOVA. To start with, I have to create the design. I don't know why I bother with its title. I don't think it turns up anywhere, but we'll put it in. Number of factors is going to be 2 here, as you saw in the Excel sheet. Double click gets me the first one, and there I can switch to the second one. Neither of the factors nested, both are fixed. Now the last column over here, contrast, is interesting, and it's not something I've looked at before. It really needs a video on its own, but if I double click in here, what I can do is create particular contrast. Now, contrast will be between levels of the factor. Now, in this particular design, there's just 2 levels in each factor, so the analysis of variance is going to extract or test all of the relevant hypotheses, so contrasts are not really relevant here. If I had, for instance, included the 3rd platform, then I could by going down and clicking in here, set up a contrast between platform 1 and platform 2, for example, or platform 2 and 3, depending on how I wanted to look at that. But I'm not going to look at that any further. Back here, and here's the PERMANOVA options menu. So, first of all, the design worksheet is the only one that I've got made at the moment, design worksheet 1, so there's only one option in there. Over here, I don't have any covariables, or what we would call covariates in ordinary analysis of variance. I could, and now you see it changed the sums of squares there. I'll get to that in a moment. I could have some of the environmental variables in a separate worksheet and use those as covariables. Okay, as you saw, when I put on covariables, it switched to type 1 or sequential, and I should also probably perhaps fiddle with the terms. So what are we looking at here? Type 1 sums of squares means that the analysis is going to extract variation due to the different terms. So let's have a look at the terms. We've got I, V, C, actually. Let's use the full names, so they're rather more informative. So that's what that one is. So it's sometimes convenient to turn that off so we get the full names. So the terms in the model are IVC, site pair, the two main effects, and then the interaction. So type 1 sums of squares, what it's going to do is extract variation due to IVC first, and then site pair, and then IVC versus site pair. Now, because this analysis is balanced, and all combinations of the treatments are included, switching to type 1 sums of squares won't make any difference here. It would if I had a covariable, because variation due to the covariable is normally taken out first, and then we would look at these factors. But if the design is unbalanced, then we'll get different results with type 1 and type 3 sums of squares. Type 2 I'm not really going to talk about because they're not used very much at all. It's really type 1 versus type 3. Type 3 extracts the variation that's due to each of the terms. Again, it only makes a difference if the design is unbalanced. If the design is unbalanced, then some of the variation can actually be assigned to more than one term. And type 3 only extracts the variation that is uniquely due to that particular factor. If you have the PERMANOVA manual, this is very nicely explained on pages 69 and 70, particularly page 71 in the figure. Okay, buttons over here allows to, for instance, change the order that the terms are, that the variation for the terms is extracted if we're using type 1 variation, and that's if we're using type 1 sums of squares. It also allows us to modify the model that's being used. So for instance, if I am convinced there is no interactive effect, I can actually, whoops, let's just remove the whole lot. I can remove that one and just test for the main effects. Now normally we would just go with the model that PERMANOVA comes up with because it's going to pick the model that is most appropriate to the design we've created. Pooling here means that I can add some sources of variation together. For instance, if I was convinced there was no interaction between site pair and IVC, I could pool those terms together. Reasons for doing this. The main reason for doing this is if there are limited degrees of freedom in a particular effect that's being used for creating an f-test. And by pooling terms together, we can increase degrees of freedom. That is the main reason. One other thing over here for the terms is that any term that is removed, that variation doesn't disappear. That variation ends up being pooled together with variation in the error term or residual term. So a video I did last week or the week before looking at ANOVA illustrates exactly that. Any source of variation that's not included in the model ends up in error. Okay, we'll come back to Pairwise Test in a minute. The permutation method. As in previous videos, I've just gone with the default because the defaults in PERMANOVA are generally the best. So for a factorial model, it will pick usually this one here, the one that's second on the list. If you have a one-factor design, PERMANOVA will recommend you switch to the first option. So, according to the manual, the first option is good approximate test, which will have type 1 error close to alpha, although with larger sample sizes it tends to be more conservative. So with reps equal to 10, that option may tend to be conservative. But this method also does not need large sample sizes to work well, so it might be a better choice for the design with just 2 replicas. It's also computationally the fastest. It does suffer from problems if there happen to be outliers in covariables, so it would not be recommended in that case. For factorial, it's the default option because it has excellent empirical and theoretical properties, and empirically yields the best power and accurate type 1 error for multi-factor designs in the widest set of circumstances. So that's why it's the default. And that's why I would opt with this one most of the time. The last one. Where are I? This method gives results highly comparable to method 2, but it relies on large within-cell sample sizes for precision. So it might be okay with reps 10, but not with reps 2. It has the advantage of being faster for method 2, but on modern computers that's really not much of an issue unless you have a very large design with lots of factors, lots of variables. Okay, the number of permutations is an obvious one, and I'll come back to that. Short names we've already looked at. Fixed effects sum to 0. What many people will not be aware of is the fact that there are 2 ways of calculating the F ratios in analysis of variance. The option here, fixed effect sums to 0, is the one followed by many of the statistical textbooks written for the biological sciences. It's also referred to as the restricted model. In Minitab, which is a program I also use for doing analysis of variance, under the balanced ANOVA in versions up to version 16 of Minitab, under balanced ANOVA there is an option to use the restricted model. Turning this off gives us the unrestricted model, and it also calculates the F ratios in a way that is like the way used by SAS and some other major programs. Now, when does this make a difference? It only makes a difference for models which have some random factors. If all factors are fixed, turning this off and on should have no effect. If all factors are random, turning this on and off should have no effect. What it does mean is if you've got a 3-factor design or more, and there's 1 or 2 random factors, some of the F ratios will be calculated differently if this is turned off versus turned on. With it on, we'll get the same F ratios as using the restricted model in, say, Minitab, if the option is available for the particular design. With it off, we'll get the same results as Minitab's GLM or General Linear Model. In most of the areas where I practice, the choice is the restricted model. Okay, so that covers everything. Here we go. Okay, so here's the Permanova. First of all probabilities are less than 0.05, so there's a significant effect of all factors: IBC, site pair, and the interaction. But what I want to highlight over here is the unique perms. It's about 250. And that's the unique combinations that Primer Permanova is able to find. And the reason it's relatively small is because there's only a small number of replicants and only 4 groups in total. And that means when we get down here, the degrees of freedom for the test are quite tiny, 1 and 4, or as you can see up there, 1 and 4. With about 250 unique perms, the smallest p-value we can get over here is 0.004. If the value calculated, the pseudo f, is bigger than all the permutated f's, the value over here will be 0.004, and it cannot possibly get any smaller. Now I'm just having a think about that, and what I'm going to do is increase the permutations, because that's one way of reducing that. But you see, it has no effect here because the analysis cannot find any more permutations. Now, for this particular analysis, it's actually okay because, as I said, we can get a p-value down to 0.004. So these can be regarded as reasonably reliable. Let's go back and pairwise tests. Now, if the main effects in this analysis are significant, then I know impact differs from control and north differs from south, and I just have to go and do the MDS plot to see exactly what's going on, or a PCO. But the interaction is also significant, so to find out what's happening there, I actually need to look and compare those 4 means. And I'll drop this back to the normal. And I can do it either by IBC or by site pair. So let's do site pair and see what we get. So here what's happening is for the impact, it's comparing north and south. They're not different. But there's only 3 unique permutations. So there's almost no way of actually testing either of these differences. The only way of doing that is to run with pairwise tests and go over here and turn on Monte Carlo tests. Now, okay, in some situations there are not enough possible permutations to get reasonable tests, so this is from the manual. An alternative to the result given in Anderson-Robson regarding the asymmetric permutation of the numerator or denominator of the test statistic under permutation. It is demonstrated under certain mild assumptions that each of these sums of squares under permutation has an asymptotic distribution that is in the form of, well, something complicated is going on, and I'll leave it there. So it's basically randomly independently drawing there. It's trying to simulate what the sums of squares might do if you repeated this over and over again. So it's not a permutation of the data, it's a kind of generation of a distribution of sums of squares we might possibly see. So from me, I'll do it, but I'll interpret the results with caution. So here we go. Unique perms doesn't change, but we get multicolour probabilities of 0.002 for comparing north and south and a large t-value. So I think I'm confident that those differ. Down here, within the reference, P.00055, T is that. I'm not confident they're different. And I certainly wouldn't have a great deal of confidence in that value there. But 0.002 is small enough. And one last run with this. Does that have any effect? Yes, you can see it does. It drops that down a lot, but that value there is unchanged. Okay, so over to here, and we're actually, before I do anything, I've got to do the resemblances. Same error. And I've pretty much gone through all the options. We're still using the same design matrix. I'll turn short names back off again. Type 3 sums of squares, so everything here is saying the same. And what I'll illustrate here is the p-values are 0.001. That's the smallest they can possibly be with 999 permutations. Because if the f value here is bigger than all the permutated or randomized values, it will be 1 in effectively 1000, 0.001. Which means, if I go back here and do the pairwise tests again, I think it's one of those. Yes, here. Sorry, a goof there. Let's do that again. I'll show you what I did wrong. I'm doing term IBC. I want the interaction. That's why I wasn't seeing as many as I was looking for. Okay. So again, 0.001 because we're running about 999 permutations. And the difference between impact and reference in north is 5.4, 0.001, so there's a big difference. But we get the same p-value down here for south, where the t-value is much higher, and that's because we're stuck with 999. This is a longer video than usual. It's going through quite a lot. So bump that up again, and p-value down here is down to 0.0. We've got to bump it up a long way. I did usually run through things first, so let's bump it up to that. And both of these t-values are still getting p-values at the limit. And that'll be because the denominator degrees of freedom here are relatively large. So I've actually got to go to considerably more permutations in order to distinguish. So even at this number of permutations, we're looking at 90,000, I'm still unable to distinguish these two p's probabilities. So I think we can say they're both different and indistinguishable and just look at the PCO. Okay, I'm going to finish that one off there, so hopefully that gives you a bit more insight into some of the options available in PERMANOVA.